Hey everybody, hope all's well. Today we're going to go over 5.3, trig graphs. So in the last couple of sections, we saw somewhat of an overview. What we started in chapter 6, or in section 6, was an overall review of trigonometry. 5.1 and 5.2 really gave us a different lens to view the same types of questions, or gave us an ability to answer those types of questions, maybe using a different method. I prefer to use the methods outlined in chapter 6 versus the ones in 5.1 and 5.2. But in 5.3 and 5.4, what you're going to see is we discuss in depth graphing trigonometric functions. And just like we did with most other functions that we covered throughout the course, whether we had linear functions, quadratic functions, polynomial functions, rational functions, log and exponential functions, after we discuss sort of the nitty-gritty algebraic concepts, we get into what's the big picture in a very literal sense. What is the graph going to look like? So we didn't do that in chapter 6. This is mainly done in chapter 5. Starts in 5.3. What are the graphs of trig functions going to look like? So before we discuss the overall picture, let me tell you that we're going to bucket these trig graphs into two major buckets. One, it pays to look at the graph of sine and cosine one way, and bucket all other trig functions, as in the reciprocal of sine and cosine, cosecant and secant, and tangent and cotangent, all in another bucket. What I'm going to focus on in 5.3 is sine and cosine, and maybe give you a small glimpse into tangent, but tangent and other reciprocal functions will be discussed more in depth in 5.4. So within the context of 5.3, let's look at slide 106. The graphs of trig functions tell us a lot about the behavior of trig ratios. So if you're ever confused as to what a trig function's graph should look like, or if I ever had to ask you to graph y equals the sine of x, well, just like we graphed almost anything earlier throughout the semester, sometimes it pays to make a small xy table and say, okay, well, x is supposed to be an angle measure. If I have an input value that's, let's say, 45 degrees, what's the sine of 45 degrees? Opposite over hypotenuse is 1 over root 2. What about the sine of 90 degrees? What about the sine of 180 degrees or 270? Right? And so on and so forth. And we can plot points and connect the dots. Now, before we get into graphing the big picture, I just wanted you guys to remember that. If you ever get confused as to what the basic graphs of trig functions look like, you could always make a table of values like we've done throughout the semester and plot points and connect the dots. That I wanted to give you before all this mathy definitional crap that is to follow. So let's take a look at the definition on the slide. First observation is that the sine and cosine functions are periodic. What does it mean to be periodic? A function f is periodic if there is a positive number p such that f of t plus p equals f of t for every t. The least such number, if one exists, is the period of f. What the heck does that mean? That sounds like a lot of math jargon and a bunch of complicated language, much more complicated than it actually has to be. What a period is, if I had to define it in one word, would be a cycle. So if you want an informal definition, period, sort of like a cycle length. How long does a cycle last? If I'm throwing in a load of laundry, I know that the heavy duty load is going to last longer in terms of time than the normal load versus the quick wash load. So we're going to see a similar type of thing happening here. We can affect the period of a trig function in a specific way. We'll see it, how we're going to do it algebraically in a second, but I'm just going to go a bit more in depth into this whole concept of cycle. What does it mean for this graph to have a cycle? The functions sine and cosine have a period of 2 pi. Sine of t plus 2 pi is sine of t. Cosine of t plus 2 pi is cosine of t. So the sine and cosine repeat y values in any interval length of 2 pi. What does that mean? That means if I had the cosine of 0 degrees, or the cosine of 360 degrees, it would be the same. If I had the cosine of 1 degree, that would equal the cosine of 2 pi, which is 360 degrees, plus 1 degree. Now, why is that? Why are we saying that a full cycle length for the sine and the cosine function is 2 pi radians or 360 degrees? Well, remember back in chapter 6, we had a concept known as coterminal. If we have coterminal angles, that means that if I were to draw them on a standard xy plane, let's say I draw a 1 degree angle here, it ends in quadrant 1, that's 1 degree. If I draw a coterminal angle to it, I would add a full rotation or a full cycle of 360 degrees, that's 1 rotation, plus another 1 degree. So 361 degrees would have the same starting and ending ray, thereby making angle measures that are equivalent to one another. And if you remember the whole reference angle approach to solving angles like 361, well, the reference triangle that would be associated with a 361 degree angle would have a 90 degree angle and a 1 degree angle. It would be the same as the initial angle that we drew. So we know that the cosine of 1 is equal to the cosine of 360 plus 1, or 361. If I had the sine of 75 degrees, that would be equal to the sine of 360 degrees plus 75 degrees. Because those two angles, 360 plus 75 being 435, those two angles are coterminal. Why does this matter? Why does this matter when I want to graph trig ratios or graph trig functions? Who cares that the cycle length is 2 pi and that the cosine of 1 degree is equal to the cosine of 361 degrees? Why is this important to me if I'm graphing trig ratios? Well, as many of you college students are aware of, unfortunately, and I don't want to bucket you, I would say the same thing with my high school students, I'm sure many of you have been very heavily utilizing the functions on the computer known as copy-paste. That Control-C and Control-V, or Control-X, Control-V if you're cutting and pasting. Hopefully you're not plagiarizing off of some site or copying and pasting some friend's homework, but essentially what we're going to see here is the period of a graph is a full cycle length. When a full cycle is over, the whole cycle just restarts and it repeats itself. So unlike the functions that we've seen before, like the quadratic functions or the polynomial or rational functions or logarithmic functions, these trig ratios are going to be cyclical. There's going to be a cycle associated with them. That cycle length is 2 pi. Now if you guys go to slide 107, you'll see what the sine function looks like. The basic sine function has a minimum height of -1 and a maximum height of 1. It starts at 0, 0. You could say it starts there. Now I'm defining this as being cyclical, and you can copy and paste it. You'll see what I mean in a second. But at 0 degrees, what is the sine of 0 degrees? If you were to ever get confused, again, let's make that xy table. If 0 degrees is my input, what would y, which equals the sine of x, be equal to? Well, what's the sine of 0? Again, you got to think back. Let me think up to my unit circle. At 0 degrees, the point on the circle is 1, 0. The x value of the point, comma, the y value of the point, and the y value of the point is related to the sine of the function, sine of theta. So at 0 degrees, the sine of 0 is 0. At 90 degrees, I have 0, 1. The sine of 90 is 1. So 0 At 90, I have a point at 1. At 180 degrees, I have a 0 again. At 270 degrees, I'm at -1. Oh, my bad. And at 360, I'm at 0 again. And that gives us the general shape of y equals the sine of x. We see that on our graph from 0 to 360 degrees. We can get that from a mini table of values that we put up if we ever get confused. We can get the table of values from special triangles. Sine of 45 degrees, put up a 45, 45, 90 triangle, you get 1 rad 2. Sine of 60 degrees, sine of 30 degrees gives you a half. So all of these things are things you guys can do to get the table of values, to put up the original picture. Now, as you guys can see, one full cycle length goes from 0 to 360 degrees. If I wanted the sine of 361 degrees, it would be the same as the sine of 1 degree. You can check it on your graphing calculator. Put in the sine of 1 and the sine of 361. Since they're coterminal, they'll give you the same output value. So we'll get the same output value here. So what is that going to mean? Since the period is 2 pi, the full cycle is this full cycle, I'm going to take this picture and copy and paste it, and copy and paste it. And you copy and paste it to the left because our angle measures can go negative as well. So in the diagram that you have on the slide, you have 2 full cycle lengths. It sort of looks like a wave. But understand, 1 full cycle length of a basic sine function is 2 pi radians. If you guys aren't comfortable with radians, get comfortable with radians. Most of your textbook homework problems will have the x-axis in radian form. So as opposed to 90, it will say pi over 2. 180 will be pi, 270 will be 3 pi over 2, and 360 will be 2 pi. And we know that if I have negative pi over 2, negative pi, negative 2 pi, the values repeat every 360 degrees. So you copy and paste the graph to the left and to the right. Now on my finals, I would typically ask students to graph a trig function, but I only need 1 cycle. I know this thing repeats itself over and over until infinity to the left and to the left and to the right. So I don't need to see a million cycles, I just need to see 1. Right? And we'll get into that more in depth as the lecture progresses. But this is the sine of x function, right? The basic sine of x function on slide 107. What does the cosine of x function look like? Well, similarly, cosine of x can be done by putting a table together, which I'm not necessarily going to do on the board. I have the space actually, I'll do it. But importantly, what I want to note here, this was the sine of x function. Let's do cosine of x in another color. So if I wanted the cosine of x function and I had no idea where to start, well, you can start by making a xy table. Where y is the cosine of x. Now if my input is 0 degrees, the cosine of 0 degrees is a 1. What's the cosine of 90 degrees, or pi over 2 radians? Well, that's a 0. Pi, or 180. At pi, I'm at -1. At 3 pi over 2, I'm at 0 again. And at 2 pi, I'm at a positive 1 again. And that's y equals the cosine of x. That's just one of the cycles. Now as you can see, the period length from 0 to 2 pi is my start and end point. They're at the same value now. At 361 degrees, I would now start repeating every single one of the input-output combo values. So I'm going to copy and paste this full cycle to the right. And I could also do the same thing to the left, because the cosine of -1 degree is the same as the cosine of 359 degrees rather. They're 360 degrees apart. Alright? So again, these graphs are cyclical. One full cycle will span from 0 to 2 pi unless we change that cycle. And we are going to be changing that cycle. But I'm giving you the basic graphs first before we get into anything fancy, so that you know at least what the basic graphs look like before we manipulate it. And again, how do we get the basic graphs? You can use a table of values. You can use a unit circle. You can use special triangles in order to be able to map all of this stuff out. Okay, so if you ever get confused as to the contents in slides 107 and 108, which give you the basic sine and cosine function, you could always put up a quick table of values for sine or cosine, plot some points, connect the dots, and see that that's one cycle. From 0 to 360 or 0 to 2 pi, you get a full cycle, and that full cycle repeats onwards to the right and onwards to the left, in both cases, sine and cosine. So next we're going to go to slide 109. And we're going to gloss over it because it's in section 5.3, but go over it more in depth in section 5.4. The tangent function, and I have it on slide 109 right on top. We'll discuss more in 5.4. You could see a lot of funky freshness happening with tan of x. Well, firstly, tan of x has a period not of 2 pi, but of 1 pi. So you get a full cycle length in pi radians. You also see vertical dashed lines on this graph. Well, if you guys remember, the tan function is a rational function because it is equal to the sine of x over the cosine of x. When we were doing the unit circle, we discussed this. That poses a bit of a problem. Why is that? Well, let's think. If tan of x is sine x over cosine x, whenever cosine x is 0, we have a problem with the domain. Okay? So whenever cosine x is 0, if 0, we have a restriction on domain. Because we can't divide by 0. So whenever cosine of x is 0, the tan of x will be undefined. We're going to have a vertical asymptote there, if you guys remember your rational functions section. And this is going to be the case actually for all reciprocal functions. Cosecant, which is 1 over sine, whenever sine is 0, cosecant is going to be undefined. Secant, whenever cosine is 0, just like tan, secant is going to be undefined. Cotangent, whenever sine is 0, again, we're going to be undefined. So you're going to have vertical asymptotes on all of those graphs. I don't really stress the reciprocal function graphs as much as I do the sine and cosine basic graphs, or versions of sine and cosine. But if I were to put a tangent problem up, you can follow the logic. At 0 degrees, the tan of 0 would be the sine of 0 over the cosine of 0. The sine of 0 is 0, the cosine of 0 is 1. 0 divided by 1 is 0. If I jump to 90 degrees, however, or pi over 2, we have a problem. The sine of pi over 2 is 1, the cosine of pi over 2 is 0. So the tan of 90 is the sine of 90 over the cosine of 90, which is 1 over 0, which does not exist. So at 90 degrees, we have a vertical asymptote, and that's what's happening here. And we see the behavior as I approach the vertical asymptote comes and goes upwards, just like we did with our rational functions. We plug in values as we get closer and closer to pi over 2, and the y values approach positive infinity. Now if I wanted a full cycle length, I could go from 0 to pi, which ends at 0 again, and get a full cycle that is broken by a vertical asymptote. This technically is a full cycle because a period of tangent is pi radians. But we prefer to represent a full cycle of tangent going from negative pi over 2 radians, which is negative 90 degrees, which is another vertical asymptote, to 90 degrees. That span from negative 90 to positive 90 is 180 degrees, or pi radians. So it's a full cycle, and we typically like to show the full cycle from negative 90 degrees to 90 degrees, or negative pi over 2 to pi over 2 radians, because it's a continuous shaped graph. It's not broken by a vertical asymptote necessarily. Now again, it depends on the style of the professor or whoever's teaching the class to you when it comes to calculus, but basic knowledge for tan functions are they look different from sine and cosine because there are places where the denominator of the function equals 0. So like any of the other rational functions, we will have places where we have to exclude values from our domain. Now, having said that, should you guys get super confused on this? No, because you can always put up the basic tan function using a table. X, tan of x. Let me put in some values. If x is 0 degrees, what's the tan of 0? If x is 45 degrees, 90 degrees, 180 degrees, and you should be able to get those values and plot the points. That'll help you on the way. Or you can use your graphing calculators. Now, before we get into basic transformations, I just wanted to show you a couple of things on your graphing calculators when it comes to basic trig functions. You can graph sine, cosine, and tangent functions using this graphing calculator, right? So what am I going to want to do? If I'm using my graphing calculator, right, I technically want to be able to go into y equals and put in sine of x, just as an example. Sine of x, close the parentheses. Now, I want to keep my calculator in radian mode. That's my preference when I'm graphing trig. Okay, so I put in y equals sine of x in radian mode. I went into mode and changed the calculator's mode to radian mode. Go back to y equals, you see that I have y equals the sine of x. If you go straight to your graph, you're going to get a busty, dusty, ugly looking graph, like the one that I just have on my screen here. Now, my thing to you guys is, if you want to succeed in graphing trig functions on your calculator and using your calculator properly, you want to go, before you hit graph, you want to go to zoom. The zoom button is right here. And then hit trig, number 7. Zoom trig. You'll see a much smoother sine function, because the calculator will put the window into, let's check the window, a radian type window that fits trig. When it says x min is negative 6 point something, that just negative 8.63. Well, what it's doing is calculating the minimum and maximum values of x based on pi. So if you think of pi as 3.14, 2 times 3.14 would be 6 point whateverness. So that's what the calculator is doing. If I want one full cycle of sine, and I know sine goes from 0 to 2 pi, I can put an x min of 0 and an x max of 2 pi, which is right above the caret top. So second caret top gives me pi. I can plug in 2 pi, and then when I go to my x scale, it actually calculates 2 pi for me. So for the scale, I'm going to do second pi divided by 4. I want it to go by pi over 4, or 45-degree increments. The y min -4 and y max of 4 I could leave. I could change that to 2. I see that on all my graphs so far, sine and cosine have a max of 1 and a min of -1. So let me hit graph now. And I see that if I even don't use the zoom, if I did zoom trig and then change the window, on an exam typically I'd want to see one cycle. So this would sort of tell you guys, hey, I'm going from x is 0 to x is 2 pi. And I'm going in increments of 45 degrees on the x-axis, and I have a full up-down cycle of sine. Right? So you can use your graphing calculators to graph sine, cosine, and tangent functions and various iterations. So again, on a test, you'd probably never get just, please give me the graph of y equals the sine of x. It would be the Arnold Schwarzenegger version of y equals the sine of x. Y equals the sine of x on steroids. So we're going to give you the steps to walk through the steroid versions in the slides that follow very shortly. So basic sine, cosine, and tan. Don't ever get confused. If your calc teachers don't want you to use a graphing calculator, plot a set of points, use the unit circle or special triangles. If they let you use a calculator, God bless, just use the calculator, plug in the basic trig values, and you'll see the overall shape. Now, as we've done throughout the semester up till this point, we know that when we start with a basic trig or basic function rather, we then start manipulating that to say, okay, algebraically, if I start changing things like we did with y equals x squared, that's a basic parabola, then we did a vertical shift, horizontal shift, stretching, shrinking. So we did all different types of movement or motion for our basic functions, whatever they were, y equals x squared, x cubed, rad x, we had all that stuff in class. We're going to see the same exact thing for trig. Look at 110. So once we know basic graphs, we can graph transformations. For example, y equals minus the cosine of x is an example. And I'll do a couple of examples. But first let me go through some mathy definitions. The definition. Sine and cosine curves y equal a sine kx and a cosine kx. So depending on your textbook, y equals a sine kx or y equals a cosine kx, right? So if those two are the one base form of manipulation. We're going to get into a bit more complicated version by the end of the class. But as you can see here, if I started off with y equals sine of x, what's this a doing here and what's this k doing here? These are foreign to me. Well, it's defined right here. Those curves will have an amplitude of absolute value of a and a period of 2 pi over k. Amplitude. Didn't throw that one at you before. What is amplitude? Amplitude is the largest value the functions will attain. You can think of it as your max value, your max or your min value. You're going to take the absolute value of a. It's the height that the graph will get from the 0 point, from the normal point. So let's say I have my sine function here. The highest value of this is going to be 1 sine of x, so that's going to be a 1. If I had a minus 7 sine of x, it's still going to hit a max value of a positive 7. So to take the amplitude, what we're going to do is take the absolute value of the first variable. On an exam, that's what I would expect you to do. If I asked you to graph y equals minus 2 sine of, let's say this was 4x. Well, I just want you to take the absolute value of negative 2 and give me a positive 2. Simple as that. That gets you full credit for that question. And that's going to tell you how high the graph is going to go. Period we already discussed. Standard period for sine and cosine is 2 pi. That's a full cycle length. For sine, I'm going from 0 to 2 pi. But when I throw a variable in front of the x, that changes this cycle length. I'm now not going to be going from 0 to 2 pi if I have a value in front of k. Okay? So the period is going to actually be 2 pi divided by k. Now, if any of you are taking physics, some people will call k your frequency. What that number tells you directly, frequency, let's say here I had a 4, 2 sine of 4, negative 2 sine of 4x. This 4 tells me that from 0 to 2 pi, I'm going to have 4 full sine cycles. So I'm going to have the up-down 4 times. Up-down, 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 and up-down. That's a frequency, which isn't in our textbooks. It's not as important within the pre-calc realm. I don't really care about frequency because this isn't a physics class. But in physics, that matters. So this 4 would tell me how many cycles I had from 0 to 2 pi. Here, I'm mainly concerned in not how many cycles I'm going to have from 0 to 2 pi, but what's the length of one cycle? That's what I want to know. How long am I going to have to travel to complete a cycle? Before, I had to travel 2 pi radians in travel speak. Now I have to travel 2 pi divided by k radians. So in the case of 4, that would mean that I would have to travel, a period would be 2 pi divided by 4, or pi over 2. That means in pi over 2 radians, before I would complete a full cycle in 2 pi radians, that would be 2 pi. Now I'm going to do the whole up-down thing in pi over 2 radians. It's going to be smushed. I'm bringing the graph in. I'm bringing it in closer. I'm not going to have to go 2 pi radians out. I'm going to only have to go pi over 2 radians out in that example. So that's what the period shift is telling me. So we can change the amplitude and we can change the period by affecting these variables. So I'll give you an example. If y equals minus 3 cosine of x, the amplitude would be a positive 3, the period would be a 2 pi. Then I say, let's graph a few examples. Horizontal shift. Alright, so before I graph a few examples, I think I'm going to actually give you another definition, and then I'll put two examples up on the board. So we discussed amplitude, we discussed period. Right? The amplitude is the change in height, the period is the change in the cycle length. Notice, the cycle length I could drag out or I could squeeze in. So I could have a full cycle in 2 pi radians, I could have a full cycle in less than 2 pi radians and squeeze it in. I could pull this out and have it in 4 pi radians or 5 pi radians, whatever it's going to be. Now I'm going to put up another slightly different version of this. Let's go to slide 111. In 111, we're going to look at y equals a sine k x minus b and a cosine k x minus b. All I did here was put in a parentheses and add a minus b. I still have an amplitude of absolute value of a, still have a period of 2 pi over k, but now I add in this concept of phase shift. If you guys remember our manipulation, when we were manipulating standard polynomial functions with vertical shifts, horizontal shifts, stretching, shrinking, so on and so forth, the reflections, phase shift is the same exact thing as a horizontal shift. So when I have a minus b here, the minus b implies a horizontal shift hs. The minus b implies a horizontal shift b units to the right. Remember, with the horizontal shifts, if I have a minus, if I'm subtracting a value from the x values, I'm moving the graph to the right. If I'm adding a b, then that implies a horizontal shift b units to the left. Now the next thing that I put up is the graphing window. Graph on the window of b comma b plus 2 pi over k. So if I want one full cycle, what that's going to allow me to do is say, okay, beforehand, my standard graphs, if I wanted a full cycle length, I would start at 0, 0, 1, 0, depending on if it was sine or cosine. Then I would squeeze out the cycle, pull out the cycle length or pull in the cycle length if I had a period change, stretch it up or down if I had an amplitude change. But now I have to physically move this graph to the left or to the right. So if I had a sine graph that went from 0 to 2 pi, let's say the period stayed 2 pi, and then I had to move it because I subtracted 90 degrees or subtracted pi over 2 radians, I had to move this graph pi over 2 radians to the right, just like we did with horizontal shifts before. If I had y equals x squared before, and now I'm doing y equals x minus 2 squared. If you guys remember, this would shift the whole graph of y equals x squared to the right 2 units. It was a horizontal cut and paste the graph 2 units to the right. Well here, let's say I'm shifting the graph pi over 2 radians to the right. Then the starting point would shift pi over 2 units to the right. And the whole graph would shift pi over 2 units to the right technically. So one full cycle length, if I wanted to graph one full cycle length, could start at b, that value, because it went from 0 to 0 plus b, and 0 plus any value is just that value. So I would have started at 0 plus b, or 0 plus pi over 2 in this fake example, which is pi over 2. And then pi over 2, 2 pi over k is the period. So if my period is 2 pi, then I was ending at 2 pi, and I want to add that phase shift to it. So I'm going to add 2 pi plus pi over 2. But if the period changed, if let's say my period now became 4 pi, okay, then I'm ending at 4 pi, and I need to add the phase shift value to it. So what the graphing window does is it allows me to take my function and kick it out to the left or to the right. All I'm doing is adding the phase shift value to the start and ending point of the graph. So if I used to start at 0 and end at the period, now I'm starting at 0 plus the phase shift and ending at the period plus the phase shift. And that's what that tells me. This graphing window is the x value of the starting and the ending point. Let's do a few examples. Should bring some of this stuff home. So let's look at the first one. Y equals sine of x minus pi over 3. That one's a little too easy. I'm going to flip it on its head. Let's graph y equals minus 2 sine of x minus pi over 3. So the first thing I would ask you guys to do, somewhere on the left, is make a mini chart that would say, okay, what's the amplitude of this thing? Well, the amplitude is absolute value of minus 2, or 2. what's the period of this thing? So this is where your textbooks might be a little sneaky. As you recall, the general formula was A sine k parentheses x minus b. The k, or constant, outside the parentheses will be what affects your period in 2 pi divided by k. Here, I have a sine of 1 times x minus pi over 3. So my period is 2 pi over 1, or just a 2 pi. Simply put, 2 pi. Where your textbook can try to trick you, and what I'm not doing to trick you here, if there was, let's say, a 2 or a 3 or a 4 outside of the parentheses, let's say I put, and don't write this down, but let's say I put in a number 4 here, right? That would just be the k that I plug in here, 2 pi divided by 4, and it would be a pi over 2. But sometimes the textbook is a little sneaky. It's not going to put the 4 outside of the parentheses. It's going to attach the 4 inside of the parentheses. It's going to say sine 4x here. That's a problem. Our format tells us that this k needs to be outside of the parentheses. So I would have to factor a 4 out to have a 1x. The problem is, though, I can't just take a 4 out of one term in 2 terms that are closed off by a parentheses. I would have to factor a 4 out of this. Now, that would mean that I would have to divide this term by 4 to get a 1x, and divide this term by 4 to get minus pi over 12. Why? Because if I were to redistribute the 4 times x is 4x. 4 times minus pi over 12 would be 4 pi over 12, or pi over 3. So again, this is a trick in some of the examples in the textbook where they're trying to trip people up, which isn't so nice, but they do it sometimes. Where if your problem had a constant in front of the x, but not outside the parentheses, you'd have to factor that constant out to be compliant with the formula that I gave you in the slides and the formula that's in the textbook. If you guys have any questions on it, you should definitely feel free to reach out. But again, the way this formula works, I need a 1x inside my parentheses. That's what I got in my original problem that I put on the board. I had a 1x inside my parentheses, right? If you don't have a 1x inside your parentheses, you need to make sure that you get a 1x inside your parentheses. And the way to do that is to factor it. Here I don't have to do any factoring. I'm comfortable. I have a 1 and then a 1x inside the parentheses, so I'm good. My period or full cycle length is going to be 2 pi. What about my phase shift? Well, I see that that's a minus pi over 3, so I know I'm going to be moving this pi over 3 units. Since it's minus, it's going to be to the right. I prefer now that people don't give me a minus or a plus, but you give me the physical direction, because sometimes people say, oh, minus pi over 3 for me meant move it to the right, but you wrote minus pi over 3, so I have no idea if you meant pi over 3 left or right. I prefer the direction. Write it out. Graphing window, GW. Well, before the graph would start at 0 and end at 2 pi. So it's not the case now. Now I'm adding pi over 3 units to the starting point. 0 plus pi over 3 is pi over 3. And then 2 pi plus pi over 3. Well, what's 2 pi plus pi over 3? I need a common denominator. I need an LCD. So this becomes a 6 pi over 3. That's a 1 pi over 3. I'm going to end this graph at 7 pi over 3. Okay? This is the basic information that I would ask on a test, on a final, to say, okay, this is 3 points, 3 points, 3 points, 3 points, and then the final thing would be, give me a big picture. Tell me what the graph is going to look like. And I'm going to walk you through a few steps. First, the graph of a basic sine function. I might actually need more space than what I'm used to on this tiny board. So work with me on this, people. The graph of a standard sine function goes from 0 to 2 pi. It hits a max value of 1 and a min value of -1. The middle value is pi. At pi over 2 we hit a max. At 3 pi over 2 we hit a min. And that's just one cycle of sine. Again, we went over this earlier in class today. This is the basic sine function. Y equals the sine of x. Now, the amplitude is going to be a 2. How does that change my picture? That means I'm going to vertically stretch this graph out to the red graph to hit a max at 2 and a min at -2. So y equals 2 sine of x. Now let's think about this. What's the sine of pi? 0. 2 sine of pi is 2 times 0, still 0. Same with 0 degrees and 2 pi, 0 radians and 2 pi radians. The sine of 0 radians is 0. Twice 0 is 0. So all my zeros are the same. They don't change. But this max value, the sine of 90, the sine of 90 is 1. Here the sine of 90 is 1, but 1 times 2 is 2. So my max was pulled up. As was every other point. For any other x value here, whatever the y output was before is now going to be doubled. So it's not like a vertical shift, it's a stretch. I'm stretching the function out by multiplying the output by 2. Now let's not forget this minus sign here. The minus sign implies that there is a reflection of y equals 2 sine x. Oh, there was my marker. That means that there's a reflection of the graph in the x-axis. So y equals 2 sine x and y equals -2 sine x look a little different. I'm going to have to reflect the red dashed graph through the x-axis because I have a -2 sine x. And again, all verifiable by doing some work with tables. Now, for any of you that might be asking, is all of this dashed and dotted line stuff needed on an exam? I'm showing you all the iterations to minimize confusion. If you're getting more confused, please forgive me. But I think it helps for you to see this breakout by step. And typically, on an exam, I actually have most of my students draw 2 sets of axes, one that shows all of this messy work, and one with a final answer. And that's what I like, because if your graph is worth 10 points, and you give me one graph that's wrong on the wrong graphing window with a bad period or whatever, I don't know where you effed up. So I can't maximize your partial credit. The more work you show me, the better off you'll be. Just hope that it's right. Now again, we start with the black solid graph, y equals sine x. We do a vertical stretch to get 2 sine x, but this -2 implied a reflection in the x-axis to go from red dashed to blue dashed. The max became the min. The min, red, became the max, blue. All the other values flipped. So you see the blue dashed line is y equals -2 sine of x. But that's not my ending graph, right? This wants y is -2 sine of x minus pi over 3. Now luckily for me, this problem doesn't change the period. So this blue graph ends at 2 pi, -2 sine of x would end at 2 pi. Minus the 2 sine of x minus pi over 3 would end at 2 pi had there not been a phase shift. So I don't have to change the period of the standard sine graph. I keep the blue line as is. The next example that I give you is going to change the period. But I just wanted to show you what a reflection looked like. Putting the minus in front of the whole function makes us reflect the original trig ratio that we were given. That's why I went from red to blue. Now how do I graph this phase shift? Well, simply put, I'm going to take this blue dashed line, which hits a max of 2 and a min of -2, and I'm going to regraph it for you from 0 to 2 pi, maybe on a slightly smaller scale. And I'm going to minimize this negative x axis because it's not really necessary. So the blue dashed line again starts at 0, 0, mins out at -2 pi over 2, hit pi, 0, maxes out at 3 pi over 2, 2, and hits a 0 again at 2 pi. That's y equals -2 sine of x. But what would the graph of -2 sine of x minus pi over 3 look like? Take this blue graph and shift it pi over 3 units to the right. So my 0, 0 would go to pi over 3, 0. Now pi over 3 is 60 degrees. Pi over 2 is 90 degrees. So I'm going to make this point shift pi over 3 units to the right. You can do that physically with every major 0 or max or min, just to map it out. Where I had a min at pi over 2, -2, I'm now going to have the min pi over 3 units later. Well, what's pi over 2 plus pi over 3? This is 3 pi over 6. This is 2 pi over 6. Together I get 5/6 of a pi. 5/6 of a pi is just before a full 1 pi. So at 5/6 of a pi, I would have now a -2. Now before at 3 pi over 2, I had a 2. Now I need to add a pi over 3 to it. So 3 pi over 2 plus pi over 3. Again, LCD is 6. So I need 9 pi over 6 and 2 pi over 6, which gives me 11 pi over 6. 11/6 of a pi, which is just shy of 2 pi. Here, so 11/6 of a pi, I would have my max of 2. I skipped my 0, which would have been directly to the left of 3 pi over 2, because I moved this point 3 pi over 2, pi over 3 units as well. And then the 2 pi moves pi over 3 units to 7 pi over 3, which we already solved for because we have the graphing window from pi over 3 to 7 pi over 3. So the blue dashed line from here, I just copied and pasted downwards to the blue solid line here. Then what I did was I shifted the graph. I did the last portion of the graph, which asked for a phase shift to get y equals -2 sine of x minus pi over 3. I won't fit the equation here. So I'll continue it here and I'll say y equals -2 sine x minus pi over 3. Didn't really fit it there either, but it's better than before. Alright, so again, on an exam, would I want to see 5 graphs, 5 squiggly lines? If you have the time, if you have the colors to do it, power to you. If you want to maximize your partial credit, yes, it's better for you. In theory, if I just see one final answer, I don't know if you put it in your calculator right, if you knew what you were doing. Typically, if you had all the axes labeled and everything done perfectly, I can't really dock points for that. But usually, people that get full credit are the ones that give me one or two iterations. They'll graph the original function, and then maybe they'll jump to the -2 sine of x. They'll do the amplitude and the reflection in one step. And then if need be, change a period. So typically, the amplitude is one step, changing the period is another step, the phase shift is a third step. So they give me 2 working graphs or 3 working graphs, and then a final graph. Right? If any other questions, you can definitely ask via email, or ask me those questions via email, and we can walk through them. The next one, by the way, for the next one I will also be showing you how to do these problems via graphing calculator to verify if what you did was right. But I want to try one on the slides, 3 cosine 2 x minus pi over 4. Oh, I didn't have to erase that, but it's already gone. 3 cosine 2 x minus pi over 4. Okay, so here what we're asked to do is again graph the function. Now, what I'm going to do is walk through all the steps. Firstly, what's the amplitude of this going to be? Well, take the absolute value of a positive 3, and that gives us a 3. What is the period going to be? A standard cosine function has a period of 2 pi, but if I have a variable in front of my x's, it's 2 pi over k. In this case, k is 2, so I have a period of pi. I'm shortening the cycle length. It's now not going to take me 2 pi radians, but pi radians to get a full cycle. Great. Phase shift. Again, I have a minus sign there, so it's going to be in the right direction. Pi over 4 units to the right. What's my graphing window going to be? Well, I know my final cycle should have started at 0, but since I'm moving it pi over 4 units to the right, it's going to be 0 plus pi over 4. The full cycle would have been only pi radians, not 2 pi radians, so it would have ended at pi, but since I'm moving it pi over 4 units to the right, it's pi plus pi over 4. So 1 pi plus 1/4 of a pi. So this is 4 pi over 4 plus 1 pi over 4, that gives me 5 pi over 4. So my full cycle goes from pi over 4 to 5 pi over 4. Great. So that's a couple of points for each one of these steps. Now I want to see the full graph, the image. Show me what it's going to look like. Step 1. Let's put up a basic cosine function. Basic cosine graph goes from 1, 0, 1 to pi over 2, 0 to pi negative 1 to 3 pi over 2, 0 to 2 pi 1. That's y equals the cosine of x. First iteration is a change in the amplitude. Fine. My amplitude is a +3. So let me extend this out to a 3. Extend that out to a -3. At the cosine of 0, I get a 1. The cosine of 3 times the cosine of x would be 3 times 1, or 3. So this max was stretched up 3 units. pi over 2 radians. So cosine of pi over 2 is 0. 3 times that would be 3 times 0. Stays a 0. Cosine of pi is -1. 3 times that would have given me a -3. So again, I see that my maxes and my mins are more pronounced. My zeros remain the same. And please excuse the blue graph going up into this description, but y equals 3 cosine of x is the blue graph. It's if I took the basic graph and pulled it upwards for an amplitude of 3 times more than what I started with. Now I don't have a reflection here because I don't have a minus in front of the 3, but I do have a change in the period. My period is going from 0 to 2 pi to 0 to pi. So in the simplest terms, what you can do is take the starting and ending points and assume that this ending point is just going to be smushed. So now I'm going to end at not 2 pi, but 2 pi divided by 2. This 2 here makes me divide every single input value, input-output combo by 2. I keep the output value, but divide the input by 2. So before I had 2 pi comma 3 as a point on the blue graph, right? This point was 2 pi in terms of x, 3 in terms of y. Now I'm going to do 2 pi over 2 comma 3. So I kept the output, I divided the input by 2. Well, 2 pi divided by 2 is 1 pi. So pi over 3 is where I'm going to end the graph. That fits, because I'm going to go from 0 to pi. 0 divided by 2 is still 0. Right? So 3 pi over 2 divided by 2 is 3 pi over 4. 3/4 of a pi is right in between half pi and a full pi. 3/4 of a pi. Before I had 3/2 of a pi comma 0. Now I divide that input value by 2. 3/4 of a pi and keep the output value of 0. Before I had pi -3. Now I divide pi by 2. I get pi over 2, -3. Before I had pi over 2 comma 0. Now I divide pi over 2 by 2. I get pi over 4 comma 0. So my blue solid graph becomes this red solid graph, which is y equals 3 cosine 2x. We see that the blue graph had a period of 2 pi. I squeezed it. I squeezed everything in now. Everything comes in to have a period of pi. So I get a full down-up cycle of cosine, full cycle of cosine in pi radians. And again, what did I do to get all these specific point values? I took the old table of values, which had inputs and output combos. I kept the outputs but divided each input value by, in this case, 2, because I have a 2 here. And it varies based on the value. If you had a value of a 1/2 there, or a 4, or a 5, you'd be dividing each of the input values by that constant to get the new input value, but you keep the old y values. That's how I think about this. The phase shift, that's the final piece, that's what's going to give me the final graph. So I'm going to graph this on a different set of axes, like I usually try to do. So here, my full down-up cycle of cosine started at 3, I'm going to take the red graph, and ended at 3, at pi comma 3. So let me redraw the red graph. Started at 0 comma 3, and it ended at pi comma 3, with zeros at pi over 4 and 3 pi over 4, and at pi over 2 we had a min. this was y equals 3 cosine 2x, the red graph from above. I didn't institute the phase shift yet. The phase shift is going to take this red graph and push it over pi over 4 units to the right. So I'm going to cut this graph, pick it up, and paste it pi over 4 units to the right. Used to be 0, 3. Now I move that pi over 4 units to the right, so it's going to be pi over 4, 3. Before it used to be pi over 4, 0. I'm going to take that pi over 4 and add a pi over 4. A quarter pi plus a quarter pi is a half pi. So I'm going to have pi over 2, 0. Now I have pi over 2, negative 3. I'm going to add a quarter pi to a half a pi, and I get 3/4 of a pi. So at 3/4 of a pi, this output value is replicated at negative 3. So I get the down cycle here. 3 pi over 4, 3/4 of a pi plus a quarter of a pi, which is the phase shift value, is a whole pi. Whole pi 0 instead of 3/4 pi 0. Now whole pi I had at 3. I'm going to add a quarter of a pi, which gives me 5/4 of a pi. And that's where the full cycle is going to end. 5/4 pi 3. And that's going to be y equals 3 cosine 2 x minus pi over 4. Alright? So just walking it through again, you have a trig expression or an equation. In order to graph this, you want to look at the implications of the constant in front of the whole term. That's going to change the amplitude or change the height of the graph. You want to look at the constant outside of the parentheses. That's going to affect the cycle length. Is it going to be longer or shorter? You want to look at the value that's being added or subtracted from the x values. That's going to change the shift or move the graph to the left or to the right. We had all of those components here. The only thing that was missing was a reflection. But typically it wouldn't throw all of those components at you on a test. This would be a perfect type of test question because it tests your ability to manipulate amplitude and period and a phase shift. So we saw how we went from the black graph to the blue graph when all we did was stretch it for the amplitude, and then from the blue graph to the red graph when we changed the period, and then from the red graph to the black graph again when we pushed it out. So those are all the changes. How do I put this in my graphing calculator without messing up too bad? You go back into your y equals. Now we had 3 cosine 2 x minus pi over 4. So I'm going to type in 3 and then cosine. Now I can't just type in a 2x here because here I had a 2 outside of my parentheses. So this is going to be weird for me because technically once I hit cosine on my calculator, a parenthesis opens up automatically. Now, what a lot of people do incorrectly, that's why I'm pointing it out here, this is a common mistake, is on their calculator they will type in 3 cosine 2x minus pi over 4. That is wrong. The 2 outside the parentheses again implies that if I were to bring it inside, I would have to distribute it to both terms. So you could either do one of two things. You could do this on your graphing calculator. 3 cosine 2x, and then I had minus 2 times pi over 4. So I would have 2 pi divided by 4. Not minus pi over 4, but 2 times pi over 4, which is 2 pi over 4. Double close the parentheses. That's one way of typing it in. Another way of typing it in, which causes less pain and heartache, is 3 cosine 2 parentheses x minus pi over 4.
and I like to be super careful with my parentheses. But you can do 2 times x minus pi over 4. And the 2 outside implies that you're going to do x minus pi over 4 first, and then multiply all of that result by 2. So that's what I would recommend you do. Because here now 2 is going to be times x minus pi over 4. So however you want to do it, you can put it in one of those 2 ways. Again, you want to hit zoom trig, zoom 7, for a prettier picture, but you're definitely not going to get one cycle if you hit zoom trig. And why is that? Because zoom trig goes from negative 8.6 to some 8.6, so it's more than negative 2 pi to 2 pi. Here we said our graphing window goes from pi over 4 to 5 pi over 4. So if I want to see if my one cycle was correct, you could go back to window, and for the x min, type in a second pi divided by 4, and then here do 5 pi divided by 4, and have your scale do second pi divided by 4. Just go by increments of pi over 4. Y min and max of negative 4 and 4 are okay because our amplitude is 3. Now when I hit graph, let's see. Well, what do you know? I'm getting what looks to be one full cycle. And it's going from pi over 4 to 5 pi over 4. So I'm getting the final black graph on my graphing calculator. I've now confirmed that the graph that I put up was correct. So again, really the only way to use your graphing calculator on these types of problems is not as a cheat, but as a, I know how to do the right work algebraically and I can check my work. Having done what I just did, put it into the y equals portion of the calculator, being careful with my parentheses, open a parentheses, put in x minus pi over 4, only before putting in a 2 times that, hitting zoom trig, fixing the window, and confirming that my black graph indeed is one full cycle. This section is not easy. I want you guys to reach out if you have any questions. Feel free, again, to reach out. And we're definitely, I mean, on a typical final, you would definitely expect to see a problem of this caliber, and it would be worth, I don't know, 25 points with all the multiple parts together. So, again, if you have any questions, feel free to reach out. Take care.